Hello and welcome to week 12. This week 12 is dedicated to CFD applications for design and performance assessment. We know we are more excited to learn CFD, and that too when we are talking about the CFD applications for turbomachinery or CFD applications for special requirement. It is of great interest to all of us. What all we have discussed in our last week, that's what is talking about need for future compressors for special application and special need. We have discussed different approaches in order to improve the performance, in order to improve the fuel economy for the engine, in order to address the issues related to achieving high pressure rise. All those aspects we have discussed with. We also were discussing about the recent trends for the development of axial flow compressor. Then we started discussing about the application of industrial fans. We have discussed about various applications. Then we have discussed about the special application of axial flow fans. That's what was followed by the design of axial flow fan for wind tunnel application. We have also discussed the design of ventilation fan. And that's what was giving the brief idea about design of industrial fans. So in this week, we will be discussing about understanding for CFD application to axial flow compressor. So always the question, that's what will be starting in our mind. That's what is why, what and how. Very first question that's what will be coming is why we want to do CFD. Now be careful, people used to make a joke saying colorful display. Yes, if you are not having detailed understanding what you are doing, and then that's what is colorful display only. So the thing is, the question of why, what and how, that need to be understood by all of us. Okay, then we will be discussing about case studies. That's what will covering different aspects which I explored personally, as well as my group. They are working at IIT Kharagpur. We will be taking some case studies. That's what will be explored by different researchers throughout the world. We will be discussing what all are the advantages of CFD, especially for axial flow compressors. We will be discussing about issues and challenges of CFD application to axial flow compressor, and what all are the next generation CFD demands. So this is what is not the class. That's what will be starting from fundamental in order to discuss the CFD. That's what is all the way different domain, and that's what is required all other kind of understanding. So we will not be discussing about the CFD analysis in sense of different numerical techniques, different equations. No. We will be discussing about what all we are looking for when we have done our preliminary design. So if you look at all 11 weeks, we have discussed a whole lot of things in sense of aerodynamic design of axial flow compressor as well as fans. Now the next step, it is to go for CFD analysis in order to achieve what we are looking for in terms of performance assessment. And we need to verify our design. What design we have made, is it okay to move forward with? So with this, let's start with. So here in this case, these are the steps what we need to understand when we are discussing about the CFD application. Let it be discussed in sense of general sense of application of CFD, as well as CFD applications to turbomachinery, CFD application to axial flow compressor. Very first question that will come in the mind, why? Why we want to do CFD analysis? So the thing is, we are looking for certain kind of performance expectations what we have designed, or maybe already available system. We need to verify, is it giving what we are looking for. So if you recall, we were discussing about the sizing problem, we were discussing about the rating problem for axial flow compressor. So that's what is coming here. Then the next thing, that's what will be coming in mind, is what all are the available resources with us. when we are talking about the design of axial flow compressor or say making of axial flow compressor, it is but obvious we need to go with the testing, we need to go with the experimentation. That may or may not be possible for many universities, maybe for many industries. Okay, under that condition, this CFD, that's what will be serving our purpose for initial first cut design. Next question, that's what is say what all we want to analyze, what all we are looking for. Now when I say what, that means I need to understand the detailed flow field study, what all are the changes of fluid properties, what will be my flow structure, and based on that we will be analyzing the loss models. Once we are able to analyze these losses, that's what is happening in axial flow compressor, that's what will be helping us in order to assess the efficiency. Now the question is, we are looking for efficiency to be higher, that means we are looking for these losses need to be reduced. So until and unless we are having detailed understanding of flow field, it is difficult to analyze those losses or to improve the efficiency. Now the question is where? So level of details what we are expecting and the problem understanding. So the thing is, we need to realize what is the application of what we are designing. Until and unless we are having the background of that, what all analysis or what all design we are doing, it is of no use. So we need to be very careful what is the application where you are applying this logic. Now after knowing all these aspects, now the question is how to do this analysis. So what we will be doing is we will be making our computational domain. Now this computational domain, that computational domain we need to discretize or we need to divide into small volumes, and that's what is called say domain discretization. Then we need to understand, say we are having rotor and stator, that's what is need to be incorporated with say interface. So we need to have the details of interface. We are looking for say size and quality of mesh. Now what we are discussing at this moment, size and quality of mesh, you can imagine we have discussed the design of say wind tunnel fan, that's what is having diameter of 4 meter. We have discussed about the ventilation fan where we were having say diameter of 0.28 meter. Now all this, that's what will be asking for discretization of the domain. Now that's what is coming into the picture. It need to be realized like how many number of nodes, how many elements we will be selecting in order to do simulation. So this is what is very important. So we need to know how to do that part. Now next, that's what is where we are applying this, or what is the use of what we are designing. That's what will be deciding with what all will be the boundary conditions. So suppose say we are designing say fan for aero engines, we can say we have an entry condition as atmosphere, my exit condition that is also maybe with somewhat high pressure rise. Suppose say we are doing our design for LP compressor, we are doing our design for say HP compressor. So we must know what is my entry condition and what will be my exit condition. Until and unless we are having this design or say detailed information, it is very difficult to analyze that part. So we need to have the idea of that. What all flow parameters we are looking for, that is also equally important. Now after doing this understanding, we have our discretized domain, we are having our boundary conditions. Now we are looking for the solvers. So solvers basically they will be solving our fundamental equations. We can say conservation of mass, conservation of momentum, conservation of energy, maybe we will be having shape of a gas equation, all those terms that need to be solved. Once we are solving that, based on that we are doing calculation of different parameters or different properties, maybe in terms of pressure, in terms of temperature, change of density, all those parameters, change of velocity, those all parameters, that's what will be coming into the picture. Now for solver also we need to have idea about what expected accuracy we are looking for, and that's what will be deciding what kind of solver we are selecting. Then we need to have idea about the convergence rate. Now the available computational resources, that's what will be putting constraint here. So we need to be limited. Suppose say if we are limited with the computational resources, under that condition we will be going with the solver with some low configuration. If we are having say very good computational facility, we will be going with say solvers, that's what is of high configuration. So selection of the solver also is very important. Now after doing all this simulation or analysis, we need to analyze our result. What we say in sense of analyzing, maybe quantitative analysis, qualitative analysis, we need to go with the validation. Suppose say experimental results are available with us, that's what will be the best reference in order to assess what simulations we have done. So until and unless we are having this data for validation, this computational analysis, that's what will become say colorful display only. Okay. Now the thing is, we are looking for available test data. Now this test data, we know the experimental part, that's what also will be having certain limitations. So we cannot go with detailed flow field study until unless we are having expensive say maybe optical tools. So with using say probes, pressure probes, or maybe by using say hot wire probes, we can do our measurement. That's what will be giving quantitative readings, but in detailed flow field, that's what will be difficult, and that's where the CFD is coming into the picture. Next, that's what is, we will be doing the checks by qualitative checking. That's what we will be doing with the numerical approach and what limitations, that's what is having the flow model selection and error analysis. So once we are having our experimental results available with us, we will be validating that with what simulations we have done, and that's what will give the error analysis, or that's what will be giving the confidence in sense of what we have done as CFD simulation. Now once all these details, that's what is available, very important part, that's what is say final outcome. So what we will be learning, how my flow, that's what will be behaving in a flow domain, that's what is giving my say knowledge base database. It will be giving us say final product, expected improvements, what we are looking for. Suppose say already designed compressor or fan, that's what we are having. Maybe we will modify certain geometries, we will be modifying certain parameters, that's what will be giving my expected performance improvement. Say recent trend, that's what is to enhance say the operating range. So what all modification we can do such that without compromising in terms of efficiency, we can move it increasing the operating range. That's what is very challenging. That's what is possible by exploring this computational fluid dynamics analysis. Now the thing is, we also must understand what all are the reasons for the improvement what we are getting by this analysis. Okay, and that's what will be helping us for the future designs. Now documentation of what all we have done, that's what is very important. So in overall, if you look at this computational fluid dynamic analysis for axial flow compressor or the fan, that's what is demanding for all these aspects, and we must realize why we are doing this computational fluid dynamics analysis. Many times people used to say this CFD is a design tool. It's a misconception. What all we have done in last 11 weeks, that's what is your design, that's what is your aerodynamic design, that's what is your preliminary design. Based on that, you are making your blade geometry. Now after making that blade geometry, you are analyzing your blades, and once you are analyzing your blade, that's what will be giving what we are looking for in terms of performance of those blades, or those rotors and stator combination, or that stage or maybe multi-stage configuration. So do not be in a misconception saying like CFD is a design tool. Rather we can say CFD is design improvement tool. Okay, there are many commercial companies, they are giving, say, you can do design quickly by putting the numbers, that's what will be generating the geometry. After generating the geometry, you can do your CFD analysis, you can check with the performance assessment. It is not that easy when we are talking about the application of special need. Be careful about all those aspects. Okay, so we need to do our own design. We need to analyze our own results, and then after you come up with the solution. Okay, so this is what is all about the CFD, how it is working and how we need to think of. Now let's move for, say, turbomachinery application. When we are talking of, it says we will be having complex shear flows. So we will be having shear layers in rotating surfaces, shear layers, that's what will be developed on the curved surface. We will be having separated flow, we will be having shock boundary layer interaction, we will be having corner separation. So all this what we are talking of, that's what will lead to have the secondary flow, that's what will be generating within the flow passage. When we say this is what is generated, that's what will lead to increase the losses. What losses we say as aerodynamic losses, and basically those aerodynamic losses, that's what is deteriorating your performance as well as efficiency. We are having our flow to be swirling flow, or it will be having vortices. Okay, the interaction with the boundary layer. So all those aspects, that's what will be coming into the picture when we say aerodynamics of axial flow compressor. Now, when we are talking about application of this CFD, there are certain challenges, and those challenges we can say that's very first thing, that's what is for the generation of grids. That means in order to discretize your fluid domain, we know our blade shape what we will be getting using different approaches, say different world distribution, that's what will be giving the three-dimensional shape to my blade. And for that we need to do the discretization, we need to do the meshing. That's what is very challenging. Next, that's what is we are having rotating domain. My flow will be highly three-dimensional, unsteady, rotating, and it will be having its own turbulence intensity. The capturing of these losses under the viscous effect, that's what is challenging. The selection of turbulence model, we can understand at the initial stage, suppose if we are looking for the flow over aerofoil, initial stage we are having our flow to be laminar flow, then we will be having transition, and later part that's what is turbulent flow, fully turbulent flow. So we can understand we need to capture all this flow physics, and that's what is very challenging. And along with that, my blade is rotating blade. So you are having rotating flow with this flow over aerofoil kind of configuration. That's the reason why challenge, that's what will be increasing. After that, we need to realize the fluid structure interference or fluid structure interaction. That's what will be giving us, say, aerodynamic loading on the blade, and that's what is coming in sense of aeroelasticity. Okay, so all this, that's what is coming into the challenge. So the analysis of, say, turbo machines or CFD analysis of axial flow compressor, that's what is very challenging aspect. So initially it says like this CFD tool, that's what was initially been developed for analyzing turbo machinery, and then people, they have found their application for different applications for aerospace, later on for analyzing different process industries. But very first CFD analysis, that's what was being developed in order to analyze the flow through these turbo machines. Now we know our axial flow compressor, our axial flow fan, that's what is having heart, that's what is aerofoil. And now in aerofoil, as we have discussed earlier, we will be having all this kind of difficulties. That's what is happening on my blade suction surface. Same way on pressure surface also we will be having growth of boundary layer because of the curvature. Now this aerofoil, this analysis, that's what is very challenging. we must realize that part. Okay. Now, in order to have say use of CFD, so this is what is one of the plot, that's what was given by SNECMA for say their fan development. So if you look at, initially they have gone with the potential flow theory, later on they have used Euler's 3D model, Navier-Stokes 2.5 dimensional model, Navier-Stokes 3D model, and based on that over the year they are able to improve the efficiency near the cruise condition. Okay. Now here if you look at, we have discussed earlier also, these are the rotor blades for fan. That's what has been developed by Rolls-Royce as well as by GE. Thanks to CFD, in order to come up with the latest blade. So here if you are looking at, these blades are say not the shrouded blade, here they are having all three-dimensional shape. And this blade what we are talking of, that may be having height in the range of say 5 to 6 feet, and that's what you need to do design with. So this computational tool, that's what has helped a lot in order to design such kind of high bypass ratio fans. Now this is what is a growth of application of CFD over the years. Initially people they were doing one-dimensional analysis, later on they have done say two-dimensional analysis, quasi 3D analysis, then later on as per the availability of computational power and detailed flow field understanding, people these days they are talking about 3D say unsteady flow field analysis. So initially we know our flow, that's what was say subsonic, later on that goes to say transonic, and now we are having say different kind of configuration. That's what we have defined as say in some region we will be having flow to be subsonic, in some region we will be having our flow to be supersonic. And this is what need to be used in order to finalize our design. Let me put, it is not used for design, this is what is to finalize the dimensions and design of say axial flow compressor as well as say axial flow fan. Now this is what is whole database, that's what is available with different engine design manufacturing companies. So different design companies, they are having all this database, that's what is available with them, and they are adopting those concepts in order to finalize their design. They are having their in-house code, and those codes they have been developed over the year with maturity and understanding with experience. So here if you look at, this is what is talking about quasi 3D. Here we are having say special applications of tool, and we are at this moment we are moving in sense of 3D Navier-Stokes, unsteady simulation, all those analysis, that's what is going on in order to do finalize of the design. Now this is what is a whole cycle. Now as we discuss, people they are going more aggressive in sense of expected pressure rise. We are looking for say axial flow compressors and fan that need to generate per stage pressure rise to be very high. Under that configuration, this is what will be acting like a black box. Now what we need to do is we will be doing say initial design or say preliminary design, what all we have discussed up till now. People, those who are working in this aerodynamic design aspect or mechanical design aspect, they are having their previous experience, they are having whole their database, that's what is available with them. With that they will be doing say 2D axisymmetric analysis, then after they will be going with say detailed analysis for say different blade rows. Suppose if you are having number of say stages to be on higher side, that's what will be analyzed based on data available for detailed design. Then they will be going for say 2D or 3-dimensional design. Again that's what will be developed and that's what will be tested with the test rig as well as say engine test. We need to be very careful. We have discussed what all are say the challenges for application of CFD. So when we are doing our analysis, that need to be validated experimentally. So people they are assuming, they have presumed that CFD will be the replacement for this experimental testing. that's what will take a long time. As on today also, the results what we are getting from this computational analysis, that's what is little tricky and challenging and questionable. Until and unless that's what has been validated with the experimental result, these results are little tricky and of question. So I'm not saying that what all we are doing at this moment using CFD analysis is of no use. That is of use, but we need to have confidence in what all analysis we have done. Being experimentalists, we are always having this as a challenge, and that's the reason, if you ask, I am more preferring towards say doing experimental analysis, and then maybe in order to understand detailed flow field study, we can go with this computational tool. Now if we look at, there are different levels of CFD analysis as we have discussed. Very first, initially people they were talking about simple Euler's or potential flow solution. That's what was a say initial approximation. Later on people they went with say 2D and axisymmetric Navier-Stokes solution. Later on people they started talking about the 3-dimensional Navier-Stokes solutions, where we are having RANS or URANS. We can say Reynolds average Navier-Stokes equation, that's what we are solving. Now here this is what is a truncated form of Navier-Stokes equation, where we are doing certain assumptions. So for the first cut design, for the initial design, people they are using RANS simulation. That's what will give the quick solution to what analysis what we are doing with. Later on, as per the expectation in terms of performance, people they are going with say unsteady RANS simulation. Now as we know, we have our limitations with the computational facility and the resources. That's what was say older story. Now people they are moving towards higher end computational facilities. That's what will give more flexibility to go with say large eddy simulations, where we are analyzing large eddies and small eddies. That's what will be giving the detailed flow pictures. But the computational facility requirement for LES, that's what will be huge, and this is what required maybe weeks or months to analyze the simulation what we are talking in sense of designing the compressor. So these tools cannot be used in order to finalize the dimensions. Detailed flow field study, that's what can be done by using this large eddy simulation or direct numerical simulation. Now this direct numerical simulation, that's what is taking into account for original Navier-Stokes equation. So there is no need for having say turbulence model to be selected with. Okay, and when we are having this kind of configuration, this is what will be giving more accurate results. But at the same time, the number of nodes required, that's what will be the function of Reynolds number, and that's what is say in sense of say square. So you can understand when we are analyzing say flow through axial flow compressor or the fan, Reynolds number, that's what will be in the range of 10 to the power 5 or 10 to the power 6, and that's what is need to be square. So that much computational facility that need to be there. So people they are going with say initial analysis at this moment with the small. Maybe in future we will be having those tools. That's what will be used in order to analyze the flow through axial flow compressor as well as the axial flow fans. Now types of simulation what we are discussing, that's what is say 2-dimensional simulation. So that's what is say for initial conceptual design phase, we can go with this 2D simulation. Mainly that's what is being used for the long blades or vanes. Suppose if you are talking about the fans or say LP compressor, we can go with this simulation where my flow we are assuming to be 2-dimensional. Okay, now this is what will be give the reasonably good results for the initial first cut design. When we are talking about say analyzing our flow through turbomachinery, this is what was a concept, that's what was given by Wu you can say in 1952. So that's what was very initial stage of the computational fluid dynamics, and during that time it was not that matured in sense of understanding. Later on people, they realized this is what is of very much need, and that's what is the initiation of development of computational tools. So in order to analyze this part, what he has done, he has taken two surfaces, one surface, that's what is say S1 surface and S2 surface. We can say this S2 surface is nothing but it is from hub to tip, and that's what we can say it is considered to be non-curvature. So this is what will be giving us details of how my flow, that's what will be varying from say hub to tip, how my flow angles are varying from hub to tip. So sometimes people used to say this as say the analysis of through flow analysis. This is what will be giving the details about through flow analysis, and that's what is called S2 surface. There is another approach, that's what is say S1 surface. So you can see like this is what will be giving the details about the flow between blade to blade surface. So this is what is used in order to analyze what is happening with say within the blade passage. Okay, so this concept that can be used in order to modify our aerofoils, how my flow, that's what is behaving on suction surface, how the flow is behaving on say my pressure surface, that kind of analysis that can be done. So this is what is defined as a quasi 3D approach. Now here in this case, say initially when people they started doing their analysis, they were doing say through flow analysis based on this S1 S2 surface, and they were doing the blade to blade analysis using this S1 surface. Now in order to analyze that for our full flow field analysis, we need to have say additional source term to be added with. That's what we'll be talking about, say acceleration or the deceleration of flow, the growth of boundary layer. So all this analysis, that's what is required, the understanding of coding, and that's the reason why the corrected source term that need to be introduced in the commercial package, that's what is very challenging with. So when we are discussing about the flow for axial flow compressor where we are having per stage pressurized to be very high, we know this is what need to be analyzed in a different way. So my entry area and exit area will be different. This is what is been analyzed by considering say streamline curvature method. Okay. Now let's see, this is what all we are looking at this moment in sense of three-dimensional analysis. So that's what will be the replacement of S1 and S2 surface calculation. Okay, we are looking for the whole flow, that's what is happening between the blade row. So here in this case, that's what is removing the assumption of quasi 3D approach what we have discussed up till now, and that's what is the limitation till 80s. Now with having say advancement in computational facility, we are able to analyze the full three-dimensional flow through this blade passage. So use of coarser grid, that's what will be increasing the numerical error when we are going with say quasi 3D approach. This true geometry, that's what is of need. The simulation of secondary flow, shock location at the entry within the blade passage, end wall boundary layer, those all analysis, that's what is possible now with 3D solvers. Okay, but the fundamentals, that's what has come from this Wu's analysis, and later on people they have modified the code in order to achieve detailed flow field study. Now this flow field study, that's what is people they are talking in terms of transient analysis and say steady state analysis or stationary analysis. So this stationary analysis, that's what is more common when we are talking about the initial design iterations. Later on, in order to understand the flow unsteadiness, vortex trading, wake interaction between the rotor and the stator, all those detailed study, that's what can be done by using say transient analysis. Okay, so this all what we are discussing at this moment, it is giving the idea about the growth of computational fluid dynamics over the years. Now, in order to have this analysis, we need to solve the fundamental equations. So, what all fundamental equations we are having, that's what is say conservation of mass, conservation of momentum, conservation of energy, and equation of state. So, this all what we are talking of, that's nothing but it is the solver, that's what is solving these equations in order to achieve the solution for the problem. Okay. Now, in order to do CFD analysis, we have certain steps that's what need to be followed with. So, here if you look at, this is what is a fan. Now, in order to simulate or in order to do analysis for this fan, we need to make the flow domain first. Now, suppose if I am considering I am having say more number of blades or I am having larger diameter of the fan, under that configuration my computational requirement will be huge. At the same time, analysis also will be taking large time. So, in order to simplify that, we have approach that's what is called periodic surface approach. Okay. So, data that's what is being transferred between these two domains, that's what is called periodic domain. We will be discussing all this in next lectures, but at this moment you can say we need to set up initial domain. After that, we need to discretize this domain both in space as well as time. When we are talking about unsteady analysis, we need to discretize in terms of times. When we need to have the boundary conditions that what need to be defined with in terms of inlet boundary, outlet boundary, periodic boundary condition, no slip condition, free slip condition, all these things we will be discussing in the next few lectures. Now, after that, we will be having solving of this governing equations at different discretized point, and based on that we will be achieving the solution for this particular domain. Then we need to analyze these results, that's what is called post processing and analysis of converged solution. So, this is what is all we will be discussing in next few lectures. So, at this moment, this is what all we have discussed today will give you idea what exactly is a need of CFD analysis and how we will be using this CFD analysis for the design purpose and later on for the performance assessment. So, here we are stopping with the discussion of initial part for computational fluid dynamics. In next lecture, we will be discussing how we will be doing this discretization, how we will be making our mesh, what all need to be the boundary condition, what all care we need to take care of when we are doing our CFD analysis for say axial flow compressor. Thank you very much for your kind attention.